topic of today's lecture is elastic stress. And so I'd first like to kind of get some idea of the background of the, have anyone, is anyone, how can I ask this? How many people are familiar with elasticity in general? Elastic stresses? How many people have seen Einstein notation? A couple of people. Oh, good. Okay, so some of you have. All right. Well, you can do. I don't know. You want? Would motion by mean curvature be better? So I could. We started with Alan-Kahn. Yeah, we can do that. So maybe we can. Okay. And then start elasticity. Yeah, I was looking at the schedule, and it actually said to do that before this, but I prepared for both. So. Okay. So let's go back to Alan-Kahn, and then we'll talk about elasticity. Because that you have the continuity. Yeah, that's right. That's right. Okay. So the Alan-Kahn equation. So I think this works much better, actually. So I agree. So we had for the Alan-Kahn equation, and as I said, this is one of the basic models for phase field theory. And the question we want to ask now is the effects of interface thickness and how to derive what is called sharp interface limits. And so the effects of interface on the evolution process, because that's a very important aspect of this whole phase field model. And then we want to talk about the connection to sharp interface. And so when we started our discussion on phase field methods, I talked about the growth of a precipitate, and I sketched out this problem where you had diffusion on both sides and boundary conditions on the interface. And I said, oh, if you do a phase field model, you don't need boundaries on the interface. You have this smooth interface. And the reason why we're interested in connecting this sharp interface description with phase field models is that in particular, sharp interface theories are kind of well understood. And in most physical systems, the thickness of the interface is much, much smaller than the length scale of anything else in the system. And so you really are in the sharp interface limit. And so it's not only well understood, but these interface thicknesses tend to be very small. So the thickness of the interface, specifically the thickness of the interface, let's say delta times the mean curvature, h, is much, much less than 1. Or if you want to think about this in terms of a spherical particle, r, is much, much less than 1. As I said, it's about 10. In many cases, in most microstructural evolution problems, it's about 10 to the minus 4. So it really is a small number. And so we want to try to see how we can connect the Alan-Kahn equation, which is up here, which basically has a diffuse interface, with a sharp interface theory, where we're kind of in this limit here. And there are a number of ways of doing it. And I want to introduce you a way of making this connection without doing any fancy asymptotic expansions. So mathematically, it's not that hard to do, and it's inspired or follows what was in the original Alan-Kahn paper. So you can find something that looks very much like this in the Alan-Kahn paper. And so let me first illustrate here what I mean by with this sharp interface evolution. So we're going to consider a spherical particle. So everything will be in terms of the radial distance from the origin. So this would be the position vector from the center of the particle. And so, So these are non-planar interfaces now. And I'm going to change the definition of the order parameter a little bit. No, I guess it doesn't matter. So, so we have an order parameter field that looks like this. That's 1/2. That's midway between the sample, between the interface. And you might think that this, in fact, kind of locates the interface of the sample of the particle. So that's at some time t. At some later time, it goes out to here. It goes out to some later time, t1, t2, t1, t2 is greater than t1. And so if you look at this, your phase, your composition, the order parameter profile has moved, right, to the right. So you would think that the particle has gotten bigger, right? So we have a particle. This is phi is equal to 1/2 of a certain radius, r, and it gets bigger at some later time. To R2. So it gets bigger. So the thing you want to, for those of you who have not seen phase field models, what you're doing here is you're looking at level curves or values of the order parameter. So you can kind of pick whatever value you want between 0 and 1, and they're level curves. If you look at them in this picture over here on the right-hand side, right? And what happens is that these level curves move as a function of time, right? And you say you know where the particle interface is by choosing a particular value of that level curve. Let's say phi is equal to 1/2. That's right in the middle of the interface, okay? Questions? No one was asking questions last time. I want questions. Okay. So you can define two partial derivatives. One of them is the partial of r with respect to t. I'm sorry, the partial of a, the partial of phi at constant r. And this follows that evolution there, right? Basically, that's the evolution of a level curve as a function of time, right? Because it's a constant. It's a constant. No, I'm sorry. Wait a minute. That's the wrong one. Yeah, right. I had the wrong one. Partial r. Yeah, right. That's right. So partial r with respect to t, a constant phi. You have another partial derivative that measures this. That's the one I wrote before. Partial phi with respect to r. Partial phi with respect to t, a constant r. Right. So you fix r. Okay. So so you have one that measures this distance. The other is kind of is representative of that distance there. And when you're thinking about the growth of a particle, this is what you typically call the interfacial velocity, right? And when you look at a phase field, when you look at your Cahn-Hilliard simulations, which you'll do, have they this afternoon maybe? Yeah. So you'll have these domains that evolve, and you fix your value of fix the value of phi, and you can measure the rate of motion of those level curves, and that's what you call the interfacial velocity. But there's this other derivative where you stay fixed in space. You stay fixed in space. Imagine you're sitting here, and the this wave, this traveling wave, this wave of phi just passes you by, and it starts here, and then the next moment you're sitting there, it increases in value up to here. Okay, so it's like a wave passing by you, and both of those two derivatives turn out to be important in terms of what we want to do. Okay, and so you can look at these basically two different ways. And so what we're interested in the motion in the level curves of phi. And in fact, what I think I've hopefully convinced you of, we're interested in the motion of phi of r and t. R is, the position, it varies with time, and t equals a constant. So it's a particular value of this phi of a half, let's say. It could be any other value if you wanted to, but let's say a half to just kind of fix ideas. And so if you take the derivative of this, equals 0, you can write this as zero, which implies that respect to t. Now this simple idea here that we're doing here for a spherical particle, right? This is still a spherical particle here. You can write this in 3 dimensions, just about as easily as I did here, and it's called the level set equation. And so this grew out of the applied mathematics community, and it's another interface tracking method where you don't track the sharp boundary, but you have a diffuse boundary of some sort that allows it to move in time and weld and weld together topological changes. It's very, very similar in spirit, but different in formulation. In the level set model, what you do is you use this equation here, and you get the dr dt from someplace else, like a solution to field equations or motion by mean curvature or something. In the phase field models, you're getting dr dt from the energies energies, or basically the Allen-Kahn equations up here. Okay. So we're going to consider again a spherical domain particle. Oh, sorry. Phi equals 1 on the inside. Phi equals 0 on the outside. Phi equals 1 and 0. And so we'll write the Allen-Kahn equation in spherical coordinates. So you'll have partial phi with respect to t. There's the mobility. M is the mobility. And so you write the Laplacian in spherical coordinates. So that becomes so you pull the derivative through. And so that gives you, so you pull the derivative through, and you get (4k over r) respect to r squared. Yeah, that minus m shouldn't be there, right? Yep. Any other questions, comments? Okay, everything clear? Everyone see that? Make any more mistakes? Okay. All right, so let's look at the first terms. Let's consider partial f with respect to phi. In the 1D case, which we've already dealt with. Case the Euler-Lagrange equation was this, right? It's the Euler-Lagrange equation. That's the Euler-Lagrange equation 1D. And we showed that if we integrate with respect to phi, you get at equilibrium. Remember this. This is how we derived the hyperbolic tangent solution that's on the board behind me, right? Okay, so this is the planar case, and here's the big assumption. Is it's sufficiently planar that okay. So let me stop here for a second. Okay, so what did I do? So if you look at this equation here, this one, what I did is to go from here to here, I just differentiated this with respect to phi. So that's all that is. But what I did is I took this x and I substituted it with r, okay? And so what I'm doing is I'm saying that this interface is sufficiently planar that the curvature of the interface is essentially flat. In other words, that I'm assuming is much less than 1. And so you can of course criticize this because this is kind of a ad hoc assumption. It's kind of motivated by the physics. We want to look at very gently curved interfaces. So imagine you don't want to look at a particle that looks like this where you have high curvature. You want to look at a particle that looks almost flat, right? And ask the question, how valid is this planar, how valid is that assumption? And if you do this matched asymptotics, what you find is that the real answer is this, that the thickness of the interface divided by r is much less than 1. But we're going to say that, well, it's very mildly curved, and let's just live with that for the time being. Okay? Questions? Okay. So after that, if you buy that, it's just algebra, really, from here on out. Because what that does is it allows you to replace this partial phi with respect to r by partial f with respect to phi by a term on the right hand side that just involves k. It doesn't involve the bulk free energies anymore. Okay, so this is a general treatment. It does not involve the bulk free energies, which is kind of nice. Because then what you can do is you go back then and substitute this into the Allen-Kahn equation. And you get 1 over m is equal to minus k squared. with respect to r squared. And then you 4k by, yeah, right, oh yeah, right, definitely. Right, okay, so this becomes, yes, so let's look at this term here, rather than rewriting everything over and over again. Let me do it this way, so save some time, save some of your pen. It's going to be equal to partial r with respect to phi. Use a chain rule, right? And that becomes partial r with respect to phi times 2 right, just by the chain rule. And that becomes 2 with respect to r squared, because these things cancel, right? Oh, dr, yeah. Right. Okay, so I'm obviously going too fast. So you rewrite this operator as dr d phi d by dr. Okay, so you can see so that becomes d by d phi. You pull this through, and that becomes 2 d phi dr times the derivative of the inside, which is the second derivative. These two derivatives cancel, and you just get that. Okay? And so now you can substitute that back into the r squared. All right. So to r squared. These two terms cancel. And you have 1 over m with respect to r. And now we want to get rid of the d phi dt. We go over to here, and we use the level set equation. So we want to get rid of d phi dt. We want dr dt. We want to know what the growth rate of the particle is. We don't care much about the... so this becomes the time rate of change of an individual level curve. We're more interested in the growth rate of the particle. d phi dr. So there's some amazing cancellations here. So that disappears. And you get partial r with respect to t over r. So the growth rate of the particle goes like 1 over r with a constant given by the gradient energy coefficient in the mobility. So to kind of put this in a more general context, dr dt goes like the velocity of the interface. Interface. 1 over r looks like the mean curvature h. Yeah, please. Exactly. 1 second. Yep, that's exactly right. You just got the whole essence of grain growth. That's right. So what it says, so I'll stop because that's a great point. So okay, so I'll stop. If you started with a spherical particle, it'll always do this. It'll always shrink. Yep, it always shrinks. Yep. So H. Oh, Jesus. Two, which is for a spherical particle, would be just 1 over R for a spherical particle. And so you get V is equal to minus 4K mH. And this is motion called motion by mean curvature. Or it's also what basically grain growth in isotropic systems. But what it really is it's an equation for the motion of antiphase domain boundaries, right? Oh, Jesus. Boundaries. In other words, exactly as I say. So this is the level curve of phi is equal to a half, and this is the level curve of phi is equal to a half at some later time, and it always shrinks. And so when you program up your Allen-Kahn equation on your computer, if you started with an initial condition, it looked like this, where you had your domain, it would be pixelated, because you're doing things on a grid. That's supposed to be a pixelated circle, okay? And if you started this with phi is equal to 1, phi equals 0, what would happen is that very quickly this would kind of smooth out, and then at some later time it would shrink away and eventually disappear. And so, and that's consistent with the fact that it's decreasing the interfacial energy. So V is less than 0 for H positive, and that's exactly what happens. Okay. So let me repeat this again. We just proved, by this kind of clever analysis, that the velocity goes like 4 times the gradient energy coefficient, which was just mentioned, which is positive, m, which is the mobility. Does anyone remember their good old theory of grain growth? You know, when you grew up in your sophomore level classes in grain growth, you probably saw this equation. The velocity of a grain is probably going to go like the mobility times the grain boundary energy times the local mean curvature, right? And so the velocity of the boundary is connected with the interfacial energy. The higher the interfacial energy, the faster the boundary moves. Kind of makes sense, right? If you have a high energy boundary, it's going to shrink faster than a low energy boundary. Look at this equation. There's no interfacial energy there. And this is one of the, if you read the Allen-Kahn paper, and this is one of the things that give you an idea of how John Kahn thought. I mean, deriving this equation and deriving the Allen-Kahn equation was not of an interest. He was really concerned about the fact that this term here does not depend upon the interfacial energy. It only depends upon the gradient energy coefficient. It doesn't depend upon the barrier between the two phases. It doesn't depend upon A. And so the Allen-Kahn equation is independent of the interfacial energy. So if you did your Kahn-Hilliard simulations, your Allen-Kahn simulations, and you changed the barrier, you get exactly the same shrinkage rate. It's kind of a good test of your code, actually. you should get the same shrinkage rate. And so this brings up an interesting question, is that I said that this model is the prototypical model for grain growth. And what people are doing when they're using this model for grain growth is that they're kind of using the gradient energy coefficient as kind of a marker for the grain boundary energy. But it's really not the energy that you get from a diffuse interface calculation. The thing that really matters is just gradient energy coefficient. And the reason why this makes sense, this is okay, is that this model really is the motion of antiphase domain boundaries. It's really not grain growth. And so these classical models, phase field models for grain growth that you'll see that are highly cited and used all the time, really aren't motions of grain growth. They're really motions of antiphase domain boundaries. By antiphase domain boundaries, you remember what I mean by a boundary where you have one value of the order parameter up here, and one value of the order parameter out here, and one value of the order parameter on the other side. Okay? But, and here's the difference between all of the Kahn-Hilliard stuff that we did. We're going to say, well, this is a nice computational model for grain growth, and ignore the fact that it's really not grain growth. Okay, and that's how good is the correlation? Also has the same interface width or it is not? Oh, does it depend upon interface width? I'm asking. Why is it in the case of interface domain boundary it is just the K and not K? Oh, the interfacial energy? Yeah, so this is, it's embedded, of course, in the Allen-Kahn equation. It's embedded in the Allen-Kahn equation. And so, so one of the things, for example, okay, so one of the things that if you look at the Allen-Kahn paper, so you take a grain boundary structure, an antiphase domain structure that has lots of interfacial area, you let it evolve, and the total interfacial area per unit volume decreases. And so you would think, therefore, that the total energy change is related to the total interfacial area times the interfacial energy. It's not. The total energy change is related to this thing. And so they were very concerned about this. And so if you look at the Allen-Kahn paper, one of the neat things that Sam Allen and John Kahn did is that they looked at antiphase domain boundary and antiphase domain evolution as you go towards a critical point. Okay, and you remember when we did the calculation for the interfacial energy, we found that the interfacial energy was proportional to the amplitude of the well, the depth of the well, was proportional to the depth of the well times the gradient energy coefficient. I think to a half, maybe? Something like that, maybe? Okay. But the important point is to determine A. So what happens is that you get towards a critical point, in this case a tricritical point, this amplitude A goes to 0. And so you basically have a handle on the interfacial energy. So all you have to do is change the temperature in your experiment. And so that's precisely what they did. They changed the temperature by a lot towards the critical point, change the interfacial energy by an order of magnitude, and the evolution process didn't change. The rate didn't change. So it was independent of the interfacial energy. Yeah. Yeah. And of course this is pretty controversial, but he was right. So yeah. Yeah. So it's 1/3. 1/2. Yeah, it is 1/2. Yeah. So let's talk about exactly the question that was just asked, which was a great question. Let's go back to the spherical grain case. That all grains shrink. 4 km over r. And so this is a separable equation. T. So let's let r be equal to some radius at t is equal to 0. So we're going to do exactly this shrinking experiment. We start off at some initial radius. And so that makes be 0. And so we end up with a law that looks like r squared minus r0 squared is going to be equal to minus 8kmt. So this is the sharp interface result. So the grain is always going to shrink. There's a minus sign here. There's a minus sign there. And this is the sharp interface result. And why do I emphasize that? Okay, and because remember the assumption we used to get to this sharp interface result. The assumption we used to get to this sharp interface result was right? So we had to assume that the interface was sufficiently planar. And so what this means is that as the particle shrinks, so you start off with and the interface thickness is this, let's say. When the particle gets down to this size and the interface thickness stays the same, you can see you have a problem, right? And so what you would expect is that when you're in this regime here, you get V goes like minus MKH, like the usual sharp interface result. You get down to here, this is probably not good. Probably doesn't hold there. So why is this important? Well, let's say you wanted to use this model to model a shrinking grain, right? And I remember I've been emphasizing this since the beginning. That, oh, well, let's just choose this interface thickness delta to be the real interface thickness of a grain. 2 nanometers, 5 nanometers. I have 1 micron size grains. I have to put 6 mesh points in this little region delta. I'm dead, right? I can barely do 1 grain, much less a polycrystalline array. So then you say, okay, I'm going to make delta over R much less than 1. So I'm going to choose R to be 10 microns. I'm going to choose delta to be 0.1 microns. And so that certainly works when R is 10 microns. But as R gets small, when R gets to be 1 micron, you run into this problem here that I just showed you here. And so even though the grain boundary width, if you had used a realistic boundary width, you wouldn't have this problem, right? And so there's this trade-off between the physics and the computations that you have to balance, and you have to realize that you're doing a bad job here. You're doing a bad job here. And so if you think about a grain growth problem, right? Well, what happens during a grain growth problem? Grains get smaller and they shrink away, right? They disappear. So you always have grains in your system where you're violating this constraint. And so the question then becomes what does this mean? Does it have an effect? And this is why you have to be careful when you're using phase field models. Okay? Questions? Comments? And this idea of checking interface thicknesses and checking against sharp interface results, that's why these sharp interface results are so important, are really kind of key to understanding what's going on with your phase field code. Okay, questions? Okay. How do you do multiple grains? That's the next item of discussion. And in fact, doing a calculation with multiple grain structure is so simple, really. And I'll show you how to do this. So let's look at 1 grain. So one grain, we had one grain, okay? I should really put it in parentheses, but I'm not going to put it in parentheses, right? Because it's really one antiphase domain, right? Okay. you get the idea. So you have a free energy function that looks like this, with a certain height A, right? And you start the system off with, let's say, phi equals 0 and phi equals 1, and it will shrink. And so you can say this is grain 1, and this is grain 2. And that's grain 2. So how do we extend to multiple grains? How do we extend this to multiple grains? And so we need, so we have grains 1, 2, ... There'll be n of them. N. And we're going to create a free energy function with wells for each grain. Each grain. Okay? And so basically, the ingredients of the model are really pretty simple. You just have a free energy surface where you create a well for each grain in the system. Okay? So you have a free energy function. This comes from some work. This is the Fang and Chen model. N. Squared. So there's no well. Okay, so if you can kind of see the hints of what we did before. Remember, we had phi squared 1 minus phi squared is equal to A. And so if you multiply this out, phi to the fourth, and so that the free energy up here looks just like the one down. The free energy up here looks just like the one down here, except it doesn't have a cubic term. It doesn't have a cubic term. Yep. And so if you look at this term, it's just a series of convex parabolas, basically. But as I said, you were asked the question about the Kalfad method, and so if you just have convex parabolas, you have to be able to take derivatives of these things every place, and so you put in a term here that allows you, smooths out the surface in this p-dimensional space, and that's what this term here. And so basically, each grain is described by a vector that looks like or continues. So you put in any of these grains, n of these grains, and each one sits at the bottom. Sits at the bottom of the wells. So let me illustrate this. So say we have 2 grains. So we have 2 grains in the system. So we have f of phi 1, f of phi 2. And so if you look at the summation, it's fourth. Equal to j. So basically the little deltas there allow you to take into account this constraint here. So this one is q is equal to 1, and so p can't be equal to q. I'm sorry, this one is q is equal to 2. Yeah, q is equal to, yeah. And this one it's 2, so p can't be equal to q. And then you do the summation once more. And you work that through. Oh, wait. And so this becomes, if you work that through, you get f of phi 1. You do the summation. It looks like phi 2 squared plus, it really simplifies down to something very simple. And that's really the idea. See, it's just a quadratic term that's the product of the two. So there are no cubic terms. No cubic terms in the And so if you look at the partial ff with respect to phi 1, phi 1, which is going to be equal to phi 1 2 squared. And so this is equal to 0. Uh, 1 and phi 2 is equal to 0. Okay? And so that's what I meant by there's a well and at each one of these order parameters. A well for each one of these vectors here. So there's a well. So we have n order parameters. And so you have n evolution equations. N Allen-Kahn equations. So you have n of these equations. And so rather than solving one Allen-Kahn equation, you're solving n of them, and each one is a value of the order parameter, a well at the bottom for each one of these wells. And so a typical plot of the order parameter field looks like this. Let's say as a function of x through a grain boundary. And you have phi 2 that looks like this. That looks like that. And so this has a well here for grain 1. And it's a well here for grain 2. And this is a half. 1.5. And so basically the sum, phi 1 plus phi 2, is going to be equal to 1. So this sum, this is true at planar boundaries. It's not true at trijunctions. So in other words, if you have grain 1, 2, and 3, you get phi equals 1 summing to 1 across those two boundaries. But here, actually, it's the sum is actually greater than 1. Okay? Questions? So I want to make a few remarks. If you ever go back into the literature, there are two models for grain growth. There's this one that I just presented, which is kind of goes back to a paper by Fan and Chen. There's another model that comes out of Germany, and it's Steinbach, Nestler, and a bunch of other people where they constrain always. Whereas in this case, in the Fan and Chen model, it's not constrained to be 1 always, and in fact, it can be greater than 1 at trijunctions. And so, basically, in this model here, where they constrain them to be 1, you get a different model for the trijunction than you do in this case. And there's an interesting paper by Nellie Moelans, Moelans, where she compared these two and showed that they actually lead to different grain growth kinetics. She actually looked at the growth of a given grain, and they behave differently. And the supposition is that it has something to do with this. And the answer is, of course, if you let the thickness of the boundary go to 0, it disappears. But you never do that computation for a finite thickness boundary. Okay. The other thing I want to point out here is when we're talking about phase Cal-Fat free energies, and we had begun the Cahn-Hilliard. We've begun the discussion using the Cahn-Hilliard equation. That had a free energy function that looked like this, and I said that, well, in most cases, free energy functions are not continuous like that, but they look kind of like this. And how do you put these together? How do you deal with these problems? Well, you add an order parameter in that direction, and you use exactly this model. You say phi equals 1 in phase 1, phi equals 0 in phase 2, and you couple the free energies of these two things, where now you move this out into phi space, where it's a certain composition, and that's phi equals 0, and that's phi equals 1. This is phi equals 1 C beta E. This is phi equals 0 C alpha E. And the free energy becomes a linear combination of these two free energies weighted by phi equals 0 and 1, weighted by phi going from 0 to 1 as you go across the interface. Okay? So that's the essence of these models that use Cal-Fat free energies. And so basically what you do is when you use these models, you'll have a conserved equation. That will involve composition. And a non-conserved equation and it's usually exactly the Allen-Cahn equation that tells you what phase you're in. What phase is present. Okay, and so you now have basically the underlying structure for picking up one of these models that use Cal-Fat free energies, as I sketched here, because you know how to do multi-order parameter systems. This is a multi-order parameter model, and if you have more than two phases, you have two. Yeah. Yes. Right. Yeah. You have P phases and Q grains. Right. Exactly. And so if you want to see lots of summations, there's this really interesting paper that Nellie Mullins had written where she went through this, and she actually wrote down the multi-order parameter model for a polyphase polycrystalline material. Lots of indices, lots of subscripts. But yes, exactly. That's right. That's right. So you could do a polycrystalline multi-phase system using this kind of model. And so we've done something similar to this. For example, to look at austenite ferrite coarsening, where you have austenite of a given composition, ferrite of a given composition in a polycrystalline array. Yeah. Absolutely. Other questions, comments? So I've told you about the fact that these things. Oh yeah, one other thing. Let's say grain boundary energies. Isotropic, and so if you look at a grain 1, 2, and 3, 1, 2, and 3, the energy of this grain boundary, the energy of that grain boundary will depend upon the misorientation of the lattice between grain 1 and grain 2. In other words, by misorientation, if you look at a grain, the 100 planes might be here, over there, and there, over there. So there's a misorientation. And so people typically take that into account by changing the parameters that sit in here. So you can put a subscript on this, and n, and so you can begin to change the mobility here in order to account for that energy difference between grain 1 and grain 2, for example. It also depends upon the orientation of the boundary, the normal to the boundary. So if I fix these two, what I'm saying by that is that if I fix these two misorientations, the energy of the boundary will also depend upon where I place the boundary if I fix those two lattices, right? And so it depends upon the normal to the boundary as well. And that has been that's putting all of these degrees of freedom together, the 3 degrees of freedom associated with the misorientation and the 2 degrees of freedom associated with the normal in a phase field model is still pretty challenging. It's still kind of a really challenging thing to do in order to get the full 5 degrees of freedom of a boundary. But what people basically do is they go into this model and they change M, they play with the heights of the barriers and all that kind of stuff in order to get some anisotropy into the problem. Yeah. Yeah. So you mean this constant M out here? Yeah. If you look at the Allen-Kahn equation, that's a good question. Here we go. It sits outside because looks like that, and it just looks like that because it's non-conserved. And so you just go down gradients in phi, the energy surface, and you don't have any spatial gradients to worry about. It's not a conserved equation. So that's an important idea. I mean, if you look at the free energy surface, it looks like this. And so the basic idea of this equation, remember, is that it's non-conserved. And so if you look at this point here, this point is going to move because it looks like this. M times that, so it's going to move basically in that direction. Whereas in the conserved case, it doesn't depend upon the point-wise, it depends upon spatial gradients. So it's a mass flow problem. And so, in fact, you can have a system that sits there in the conserved case, and nothing happens. In fact, you do that. You quench, and the chemical potential is uniform, and nothing happens until you give it a little fluctuation. Okay? Yeah. That's right. Yeah. Right. Yeah, that's right. Exactly.
Why not do it in the K1, K2, etc. and do it here?
You could do that too. You could do and so the trick in these grain bound. So what Guru was talking about is I very quickly kind of said, oh, M1 and Mn, right? And so if you think about what's going on, you can actually make M some function of phi 1, phi 2, ... So it's some sort of combination of the two as you go across. And so what it means is that you have M1 here, you have M2 here, and then you get some sort of linear combination of the two as you go through the middle here. Yeah, you can do that as well. So the trick in terms of these models is coming up with a system where you can put in enough physics that you understand where it's going on. But yeah, that's right. So M then would be varying across the boundary. Yeah. Other questions? This whole issue of putting in anisotropy in the context of grain growth using a phase field model is still people are still working on this in the community. But the isotropic case works quite well. And when we reconvene, I'll show you an example of what it looks like. I have a simulation on my computer. Okay? Questions? Okay, great. Coffee time. So I will see you in about 11:30, right? Yep.